Hello and welcome to the Bayesian Bake-Off. This is a collaboration between me, Alan Downey, and Ricardo Vieira at PyMC Labs, and we are going to do a bake-off. And what that means is an adversarial collaboration comparing grid algorithms and PyMC doing an MCMC algorithm. Adversarial collaboration is the best idea in science since the randomized controlled trial. The idea is that each of us will advocate for our method, and then we will do a comparison. So we'll solve the same problem, me using a grid algorithm and Ricardo using MCMC, and we'll see how they compare. So I'm Team Grid. I used to be a professor at Olin College. I am now a curriculum designer at Brilliant.org, and I'm the author of Think Bayes. And I'm going to have Ricardo introduce himself during the second part of the talk when he takes over. And that's the plan. I'm going to pose the motivating question. I'm going to show my solution using a grid algorithm. Ricardo will take over and present a solution with MCMC and then outline the pros and cons. So the problem here comes from a book that I was working on about a year ago called Probably Overthinking It. And chapter 12 starts with this quote. It says, if you're not a liberal at 25, you have no heart. If you're not a conservative at 35, you have no brain. And nobody actually knows who the author of that quote is. But the underlying question is, do people become more conservative as they get older? So to answer that, I got data from the General Social Survey, and they have been sampling the adult population of the United States since 1972. At this point, they have interviewed more than 72,000 people over that interval. During each period, they come back and they interview a different group of people. But they ask a common core of questions. There are about 120 questions that have been asked consistently since the beginning. And I was looking for the questions that would distinguish between people who call themselves conservative and people who call themselves liberal. What I found were 15 questions where that difference was as big as possible, and questions that were asked most consistently over the period of the survey. And these are the topics of those questions. And if you guessed, in the United States, what distinguishes conservatives from liberals, you will not be surprised by this list of topics. What I've reported here is the percentage of people who answered these questions and gave the conservative response to each question. And the red dots here show the people who self-identify as conservative. The blue circles are people who identify as liberal, and the purple triangles are moderates. Not surprisingly, conservatives are more likely to give the conservative response to each question. So that's the starting place. However, there's a problem with the data, which is not everybody was asked all 15 questions. That would be ideal, but some of the questions were added or removed from the survey at various points in time. And for each respondent, they get a random subset of the questions. So we have to figure out a way to fill in the missing data. Now, one possibility, the simple version, would be to just average the responses and either count the number or the fraction of conservative responses out of the 15 questions. The problem with that is that some of the questions are what I'm going to call more difficult than others. And what I mean by difficult is that people are less likely to give the conservative response. So for example, at the top here, the question about sex education in schools, at this point, nearly everybody thinks that there should be sex education in school. So that is a difficult question because only someone who is quite conservative is likely to give the conservative response. And then at the other end, there are questions that are easier by this definition of easy in the sense that most people give the conservative response. So we need to adjust for that in some way, because if one respondent gets all the easy questions and another one gets all the difficult ones, we would have an inaccurate estimate of where they are on this conservative to liberal spectrum. This is where item response theory comes in. This is exactly the problem that IRT solves. What it does is it assumes that each respondent has an efficacy, which in this case is their inclination to give conservative responses. And each question has a difficulty, which is in some sense how hard it is to give that conservative response. From that, we can compute the probability that a person with a particular efficacy gives a conservative response to a question with a particular difficulty. And this is what that equation looks like. The log odds of a conservative response is just the difference between the two. So if we're given the parameters, we can use IRT to get the probability of the data, but we're trying to go the other way around. We are given the data and we would like to estimate the parameters. So how should we do that? And this is the part where Thomas Bayes gives us a kind of disappointed look and says, really, because this is exactly the problem that Bayesian statistics solves, which is that we can use the data to compute a posterior distribution of efficacy for each respondent and a difficulty for each question. And then to fill missing data, we can compute a posterior predictive distribution for any unanswered question. So that is the plan. To do this with MCMC, you would simultaneously estimate all the parameters. There are, however, a lot of them. We have one difficulty for each question, so that's 15 parameters for the questions, and we have almost 72,000 respondents with enough data to estimate. So that is a large parameter model. What I'm going to present now is an approximation to this that I did using a grid algorithm, and then we'll do the MCMC version and see how they stack up. So here's the idea. We have a lot of data for each question and only a little bit of data for each respondent. And so I'm going to make the approximation that because we have so much data for the questions, I'm just going to estimate their difficulty using a point estimate and treat it as a deterministic known value. For the respondents, we only have between 5 and 15 questions that they answered. That's a very small amount of data for each respondent. So that's a perfect use of Bayesian statistics to quantify how confident we can be about those estimates. Let me pause here and say that you can get the slides that I'm presenting now at that URL, tinyurl.com, and then it's the Bayesian bakeoff, BBO 1123. That includes the notebook that I put the grid solution in, and that runs on Colab, so you can start up the notebook and run all the code. Ricardo has done the same with the MCMC notebook, and we have a link there also to the repository where we will store all of the materials for this talk. So let me explain the grid algorithm using a bunch of NumPy arrays. The formulation here is we have respondent I and a question j, and we can compute the probability of ij, which is the probability that respondent I answers question j with a conservative response, and it is the xbit function of the difference between those two. So if we imagine someone with efficacy 0, which is right in the middle, kind of a neutral efficacy, we can compute the difficulty of question j by computing logit of those probabilities. And let me show you what that looks like. So this is for each question, the difficulty of giving the conservative response. And these are the point estimates that I was talking about a minute ago. So that's what now, switching from math notation to code, I'm going to call the Ds. And the Ds is the array that shows these difficulties, and it's a linear array, one for each question. So we've estimated 15 parameters. We only have 72,000 to go. The nice thing is that now we don't have to run one gigantic model with 72,000 parameters, we can split it up into 72,000 models with just one parameter each. So we're going to estimate the posterior distribution for each respondent independent of each other. We'll come back and revisit that simplification later. But that's the idea. And the nice thing about it is that now I can update all of the respondents with one big array operation. So I'll give a quick outline of how I did that, and then the notebook has all of the details. I've got a prior for each respondent, which is weakly informative. It's a Gaussian distribution between -6 and 6, and it represents the prior information that we think most people are probably near the middle of this range, and that people who are really extreme are relatively rare. So that's the prior. Because there are only two outcomes in the data, it's either a 0 or a 1, either a non-conservative or a conservative response, we can pre-compute the probability of the data for all pairs of efficacy and difficulty, and that will help with making the computation efficient. Whenever I hear for all pairs of values, I think about NumPy mesh grid. So I make a mesh grid that represents all pairs of E and D. And then capital P here is an array that contains the likelihood of the data for each question and for each hypothetical value of efficacy. So one row per question, one column per efficacy. Q is the complement of P, just pre-computed for convenience. Now we get to the hardest part of the problem, which is computing the likelihoods in a great big three-dimensional array with one row per respondent and one column per data. So that's the same shape, one column per question. So that's the same shape as the data. And then the third axis is the hypothetical values of E. So we're going to compute the likelihood of the actual data for every respondent and every question. Here's a little bit of a mess to fill that in. What it does is it looks for the three possible values, either conservative response, liberal response, or a NaN representing missing data. And for each one, we're going to fill in either P, which is the probability of the conservative response, Q, which is the probability of the liberal response, or 1. And 1 is there because it's the identity of multiplication. So when we do the multiplication in a minute, it means that the NaNs will contribute no information one way or the other, which is what we would want. Finally, we can do a Bayesian update. And this is what that looks like. We're going to take all of those likelihoods and multiply them together along the question axis. So the 15 likelihoods, one for each question, get multiplied together, and then multiply that by the prior. And that result is, as usual, the product of the prior and the likelihoods. If we normalize that, that will be the posterior distribution, and that's what the second line of code here does. It normalizes row-wise. And this is a bit of NumPy hackery that I won't get deep into other than it normalizes the rows. So the result now is an array of posterior distributions where for each respondent, we have one column for each efficacy, and we now know the posterior probability that that respondent has that efficacy. So I think that was a lot of NumPy shenanigans. The point of all of this is that we can update 72,000 models in parallel, and by using these array operations, it's pretty fast. This whole thing takes less than 1/10 of a second on a very ordinary CPU. The last piece of this is to do missing value imputation, and we get that from the law of total probability, which is to multiply those posteriors by the probability of giving a conservative response and adding them up. And what that gives us is a predictive probability for each respondent. Again, it's 1 row per respondent and 1 column per question. So this is now based on the posteriors. I have a prediction for every question about what I think that respondent would answer. And then the last line here uses np.where to fill in any place where there's missing data. I will pull a value from the imputed missing values. And any place where there is data, I'll just keep the data. That is the end of the computational part. Coming back to the question that we're trying to answer, what we can do with the filled in data now is to estimate how conservatism has changed over time and how it has changed within these different groups, people who identify as conservative or liberal. And here are 2 graphs that you'll see in the notebook if you want to see where all of this goes. One of them shows that the number of conservative responses has been going down consistently over the interval of the survey. In the early 1970s, people gave conservative responses to about 8 of the questions on average. By the most recent data, that has dropped to below 5.5, just a little bit more than 5. So pretty substantial change over the roughly 50 years of the survey. And that's happening in all 3 groups. People who are liberal are becoming more liberal, but people who identify as conservative are also becoming more liberal over time. So that what this gray line shows is that if you took somebody from 1972 who was an average liberal then and brought them to the year 2000, they would be indistinguishable from a moderate. And if you brought them to the present, they would be indistinguishable according to how they answer these questions from the average conservative in 2023. So I will stop there and hand over to Ricardo. All right, how long did that take?
Not too long, I think it was good.
Okay. I felt like I definitely got into the weeds on the NumPy stuff. I hope people will kind of take it as, if you get it, great. And if you don't, you can go back and get as much detail as you want. I don't know. I might have heard by getting into it as much as I did.
I think it's a more technical audience. They have the notebook, and then because with PyMCon there's the discourse. And if somebody comes to this 3 years later and they have a question, they end up just asking. So more leeway for folks to get into all that.
Okay, sounds good. Ricardo, take it away.
Okay. Let me then share. Wait, let me take 2 notes.
Mute myself.
Yeah, that's fine. So I'll share now. The right screen, hopefully. F5 is not present on the browser. That makes sense. Okay. All right, so I'll start. I guess I should introduce myself, yes. So I'm Ricardo. I'm a PyMC developer, PyTensor developer, and a big fan of Bayesian methods and Bayesian probabilistic languages. And I work full-time at PyMC Labs, where we try to bring...
Have you read it? Put your slide. You should put your slide up, and then talk.
But the slide is back. Okay, yeah.
No, but just put the. It's okay. Just slide.
Yeah.
Back to the back slide. Then just skip. Don't talk. Skip over and start again, and we'll get it.
It's fine.
I want you to look as good as possible.
Just change the slide. Yeah, that's good. Sure. All right, I'll start again. So hello, folks. I'm Ricardo. I'm a core developer of PyMC and PyTensor. I'm a big fan of Bayesian methods, both computationally and the theory behind it. And I work full-time as a data scientist at PyMC Labs, where we try to bring Bayesian methods, and specifically PyMC, to industry. And I will take the other side of this bake-off. Obviously, I'll be a bit biased. I will suggest that MCMC, specifically the one implemented by, well, actually not by PyMC, as we'll see later, but is the same ingredient under the hood, is a good kind of tool to get to solve Bayesian problems. And it's a good tool and a bad tool, and I will get that to the end. It's a good tool because it works very well. It's a bad tool or not a bad tool. It's a complex tool, so it's likely that most people will be using it won't really understand how it works. And that means that in my slides, unlike what Alan did, I cannot show you the step-by-step how we arrive from input to the Bayesian posterior, because it's way too complicated for, let's say, 30 minutes. So let's get started. So Alan said, and I think it's fine, that actually, if you do this approximation and you no longer have the, let's say, the difficulty parameters to estimate, now you have just the respondents, and you have 70,000 of them, which is a lot, but you could treat them as just separate models with one parameter. Now, this is, it is fair, but it raises one immediate question for someone who is familiar with more sophisticated Bayesian models, or even just thinking about it, let's say, common sense is, shouldn't I learn something if I do this questionnaire and I interviewed 71,617 people? Won't this tell me something about the next person that I'm interviewing if he only answers a subset of the questions? And this, obviously, it's symmetrical, right? The point being that after you observe so many responses, you get knowledge about the person, everyone that didn't answer, because you can get pretty good estimate about what they would have answered if they were given the chance. Okay, and this will lead, obviously, to an hierarchical model where we just allow some form of information or prior belief to be shared across participants. We'll get to that. And more a bit hackish or less, well-founded is, do we really need to look at 71,618 people, right? It's a lot of responses. Actually, there's probably repeated responses there, right? Because people responded between 5 and 10, and there's some consistency. The point being, maybe looking at a subset of people will allow us to still learn all the interesting trends we care about, while keeping the problem feasible for MCMC or whatever a more heavy algorithm we are doing. And so this is to say that we won't get rid of the trade-off. We will navigate the trade-off a bit differently. We will reduce data to allow us to ask perhaps more sophisticated probabilistic questions, and we'll get to that. So first of all, as I alluded to, let's go hierarchical. So this is a very common kind of model that you can write in PyMC or in most probabilistic languages. I will not go over the details too much, but the idea is when we have data that's not nicely squared, which is our case because not everyone answered every response, usually you want to put it in a long format, which means let's just have one row per observed response. So we keep the ID, which is who was asked, what question we asked them, what answer they gave, and I'll also keep the year because I will want to use these in a more interesting model just after this one. So I will write the model. Here is already model 2. I guess model 1, if you go to the notebook, is the one without hierarchical structure. So the one most comparable to the one Alan said, where every participant is kind of unshared. Or actually, no, I don't know why I call this M2. This is the simple model. Ignore that. So in good, in good programming style in PyMC, we'll use coordinates so that all our variables have nice interpretable meanings, which means unlike what Alan showed, we won't be doing stuff with dimension 0, 1 and figure out what disappeared and what goes where. That's one of the things we try to make with PyMC. So the way I do is just I will have a normal prior for the difficulty of each question. Unlike in the grid approximation that was just shown, we will try to infer what the difficulty of each question is. And then I will have the prior of efficacy for the respondent. And actually, it's hierarchical. I was confused. Where we'll have the E will be the respondent efficacy, or you can think about the degree of conservatism or liberalism. And we'll give a normal prior for them, which will have a mean centered around 0, and there'll be a standard deviation. And we will also infer what this standard deviation should be. So we won't just say it's like 4, which was what in the unpool model or in the grid approximation was used. We'll give it a prior, will be a half normal with a sigma of 4. And then it's exactly the same formula, the same likelihood that Alan showed. So we'll have the logit of the difficulty will be efficacy. And here we are indexing with our long row of IDs. So this would be 0, 0, the first 2 rows, because the first 2 questions are the participant with ID 6. And then 12, 12, 7, 3, whatever. Minus the difficulty, and then again with this fancy indexing of the question category. Okay. Once we have that, we'll pass them to our likelihood or our observed variable, which is a Bernoulli. People either respond 0 or 1 given the logit probability, and we pass our data. So our observed is the column of answers. Okay. On the right, we have the graphical representation of the model, and importantly, you can see that, as I said, we reduced the data set, so we won't have the many respondents originally. We'll only look at 47,000 of them, which I think will still be enough, or will tell us a lot about all these participants. Will tell us about participants that were not included if we just had to guess what they didn't answer. And we'll also be able to learn the difficulty of the questions. So when Alan was talking about the fact that when you write it in NumPy code in the grid approximation, you can basically evaluate the posterior in parallel for everyone. I was thinking of another kind of parallelism, which is GPUs. So these beautiful, very sophisticated machines that can just compute many operations in parallel. And we can use that in PyMC in a different flavor, which is our likelihood is going to have many computations that are shared or parallelizable. And we can easily benefit from that by, 1, having a GPU. If you are going on the collab, you can change the runtime. And 2, making use, and this is something that I think is very neat in the PyMC ecosystem, we can interface with other libraries. So we can interface with a NumPy library, which, among other things, implemented the nice nuts MCMC algorithm in chunks, which can run on the GPU. So many layers of kind of complexity and abstraction, but for us, it's just this single line of code will allow us to get sampling that I think on my CPU would take like an hour down to 5 minutes, probably even less. So we press Control Enter. If you are in a notebook, you get sampling started, and then we can get some posteriors, and we can get to the difficulty for each question. We can get standard deviations, so this sigma parameter, so the prior kind of uncertainty about the participant we didn't observe, which is quite reduced from 4 to around 0.9. The question difficulty obviously are very similar. I'm not sure if we're going to have that plot, very similar to what Alan used with the summary statistic, because like I said, there's enough data to really tell us the difficulty of each question, because even if people responded to only 5, 10 of the questions, we have thousands of answers for each individual question. So in this part, to try to give an idea of how the two kind of approaches change, I will look at how we change at the level of the individual, because I think that's a bit more, I don't know, intuitive and perhaps more interesting. So we'll just look at two individuals. Individual ID 5034, which replied to a bunch of questions, not all, but many, in the year 1975, and individual 309, which in 1972 replied simply yes to a premarital sex question, which I think was slightly more conservative than liberal, if you look at the average of everyone. Okay. And what we'll do is basically check what does the model believe would have been the response for all the questions. And this is not exactly the imputation that Alan showed, because I'm also just kind of resimulating the responses that the participants already gave. I could just have merged the two, but this was less code. So this is like, imagine we ask a very similar question, what would the model believe? A question with the same difficulty. Okay, so on the top row, we have the unpool model, which I didn't show, which was M1. And we see that for the individual on the left, it predicted a 7.7 average conservative responses with some uncertainty between 3 and 12. Whereas for the person who responded to only one, it actually suggests 11 conservative responses, which is quite high, maybe like percentile 70, 80, don't remember exactly, and so anything between 3 and 15, of course. Now, the pooled model is going to really make us much more skeptical about this one fellow that responded to a single response. And then in this, we see that the prior or the prior predictive is, the posterior predictive is very shrinking towards kind of the average of 70.8. And that's the nice feature of the hierarchical model, right? Is allow us to be still take into consideration that this one fellow responded to a slightly conservative-like question in a conservative-like manner, but he only gave one. Will maybe discuss later if we had to actually bet money on what this fellow responded to the other questions, what we would have done. But this is what this model does. And it's similar, or at least the unpool model is similar to the one Alan did with the grid approximation. With that caveat, I said that we are not merging the one that was actually observed. Yes. I think I gave all the text. Okay, so those first 5,000 parameters were tough. We had to click the button, we had to get the GPU, we had to write in PyMC, which takes some time to get used to. But now the sweet thing is we have them all. Why not just add a couple more? And we can add, and by a couple more, I mean some that I think are very interesting. Can we add some parameter that will kind of tell us or model this change in conservatism over time that we observed? And one that I will not show, but it's in the notebook for those who are curious. Can we also add some parameter that will reflect the polarization change over time? So people giving more distinct responses as time changes. So I'll focus on the first, model 3 conservative trend over time. The nice thing is exactly what we had before, except there's one new variable called conservatism year effect, which has a normal prior, and it just shows here in the probability that people will respond yes or no to the questions as kind of a slope. So the number, the parameter times the year the question was asked, from 0 to I don't know how many years there were, 30, 40. Okay, so if it's a positive number, it means people were giving more conservative responses over time. If it's negative, it means less. And we sample. It was almost the same speed because it's the same model plus one parameter. And we get a posterior for the year effect that's negative, quite confidently away from 0. And now we can look again at our two fellows, our illustrative fellows, and remember that they were, both of them were asked quite early, so 1975, 1972, that's a long time ago. And so our model believes that these two individuals are more likely to have been conservative than if they had given the same responses today. And we can see that mostly on the individual 309, whose posterior predictive for the number of conservative responses gets shifted to the right a bit from 7.8 to 9.2. Still not as extreme as when we just had the completely separate models where it suggested 11. But so it's a model, a slightly more sophisticated model saying, okay, he only responded to one, but he was answering in 1972. So maybe there's a bit more evidence that he was a conservative fellow. And this, I think, is really basically the essence of what I wanted to emphasize with using MCMC, and not MCMC per se, but once we have a model and we have a fancy algorithm and a fancy computational backend that can take care of that, we can focus on really asking the questions, the slight tangents that are interesting in the problem. And we can also just do some nice summary statistics. So this is what the last model predicts for the average of all the questions if you were to ask a fellow that you didn't see any response to in 97 to 2020. So it learned that people were giving less conservative responses. And we can also look at how that changed per question. Okay, if you want to get into the details how I got these plots, you can look at the notebook. And with that, that was what I wanted to show. I will just summarize a bit the pros and cons of the two different approaches. I will talk in the behalf of Alan, so that will be unfair, but to make it more fair, I will not be very critical. Also because I don't really have, despite the bakeoff intro or the team, I don't really have anything against grid approximations, on the contrary. But so let's just kind of give it a summary like this. So pros and cons of the grid is definitely it was quite fast. When we compare to the MCMC, we're still talking on the order of 5 minutes using a very expensive GPU that I didn't have to pay for because Google allows you to use it for a while on Google Colab. Definitely, if you have something that's fast, you're much easier to kind of increment on your modeling process and develop iteratively. Even if you are working with a fancy MCMC algorithm, I always suggest just look at a smaller subset of the data, try to start with the simpler models because they will also sample faster. Maybe use some approximations in the meantime. Just be aware of all the tools that are there that give you something. In the end, we're always approximating one way or another because we can never compute that damn integral on the denominator. The error due to this discretization, which is the thing you have to worry mostly about in grid approximation, is negligible in this example, and in many others if you stay to a few variables. But you usually have to simplify a bit the model to indeed stay in this realm of a few variables so that you can still basically use the grid approximation. MCMC, I would say, one, it was fast enough. If you have a model that you already care about, you know, it's well specified, makes mathematical and conceptual sense, you can then use, you know, the benefit of the whole 2023 computational stack to get it to sample faster. You don't need to simplify assumptions as much. I mean, there's always simplifying assumptions. You're always specifying priors that you don't really believe or likelihoods, but you can do less. It very naturally extends to hierarchical models, to modeling linear trends, other sophisticated effects, as long as you have some input data that you think could be relevant to the problem. On the other hand, not fast enough. Not fast enough compared to the grid we use here, but more generally, sometimes not fast enough compared to what folks expect or need in other, let's say, machine learning approaches or even Bayesian approaches like variational inference and stuff like that. So in our case, it was not fast enough, or I didn't have patience to wait 20, 30 minutes to sample, so I reduced it to 5K respondents. And one of the cons I alluded before is you get a lot of power and you can sample like thousands of related variables together, but now you have a very complex machinery under the hood, and sometimes it breaks or sometimes it doesn't work well. And now you have to try to understand where the problem is, and that can be a job in and of itself. I think that's what I wanted to say.